Hello and welcome to ElectroPHY channel. In this video we are going to talk about Lorentz force. According to Lorentz Force Law, force can be applied to a particle of charge in two cases. First, when it is in an electric field, and second, when it is moving and it is in a magnetic field. Force is calculated based on this equation. Now let's consider a special case of Lorentz Force Law. In this case, Lorentz Force Law says if a magnetic field is applied to a wire with current goes through it, the wire experiences a force. This equation is a special case of the general one said in previous slide. Now we are going to talk about some details and a special example. The current which goes through a long wire makes magnetic field around the wire. If the wire is long enough, magnetic fields will give the shape of circles which are surrounding the wire. As we get further, our radius of circles get larger, magnitude of magnetic field gets smaller. The direction of the field can be recognized with right hand grip rule. If thumb of right hand shows the current direction, other fingers will show direction of magnetic field. With the Fleming's right hand rule, the direction of Lorentz force can be understood as well. The thumb shows the force direction. Now the special case, two straight parallel wires. Two straight parallel wires with the same current direction attract each other. B1 is the magnetic field of I1 current and F12 is the force applied to the wire number 2. The magnitude of the force is proportional to the current's value. We have done parallel wires experiment. In the left picture, no current is applied to the wires, and there is no force between the wires. In the right side, the current goes through the cables, and you can see that cables with the same current direction attract each other. Two straight parallel wires with the opposite current direction repel each other. B1 is the magnetic field of I1 current and F12 is the force applied to the wire number 2. The magnitude of the force is proportional to the current's value. In the left picture, no current is applied to the wires, and there is no force between them. In the right side, the current goes through the wires, and you can see that wires with the opposite current direction repel each other. Here, transformer terminals are shown. As you can see, two parallel wires are connected to each terminal, which their ends are connected, so the secondary of transformer is shorted. It is good to know about our experiment setup. Our setup consists of an autotransformer in series with a transformer. Autotransformer helps us to have continuous steps of AC voltage. It helps us to control the current going through the wire to have different amounts of force. Also, to prevent the increasing temperature of wires, we have to be able to control the current. Transformer helps us to change the voltage and the current level. The formula of an ideal transformer is shown. In our test setup, we used a transformer in which the secondary voltage is 10 times smaller than the primary and the secondary current is 10 times bigger than the primary. In this way, we can make sure that the small current drained from the line power doesn't exceed the maximum value. Special thanks to Professor Mohseni, great master of Tehran University, because he helps and lets us record these videos. Thanks for watching. Hope you learned good things. If you like this video, hit the like button and subscribe to support our channel and get more like this video.